Hey everyone, so today we're going to be talking about the units of circuits, is sort of what I call it. So far we've talked a lot about circuits in general, sort of an introduction to circuits, how to draw them, what they look like, what they're composed of. But today we're going to be talking about the units of measure or measurement that exist in circuits. Not all of them, but we're going to be talking about a few. And as we get going into this lesson, we'll go into more detail about current, resistance, and voltage and what they even mean. So the very first thing we're going to be talking about is resistance. Resistance is measured in ohms, and so there's a relationship between resistance, voltage, and current within a circuit, and that relationship is known as Ohm's Law. And so this little triangle right here, hopefully you can see my cursor, that's how we represent Ohm's Law. Now, you've seen these triangles before. We've used them when talking about density problems. We're going to be doing some math problems again today that involve Ohm's Law and are new units. So according to Ohm's Law, I, which is current, we'll get into that, is equal to voltage over resistance, or voltage is equal to current times resistance. And finally, resistance is equal to voltage over current. So there's this relationship between these three different things that allow us to calculate sort of missing variables when we're looking at a specific circuit. Here it is again, so V equals IR, which is voltage is equal to current times resistance, and then over here they've just rearranged the formula. So resistance, the unit of resistance is ohms. So sort of like a unit of distance can be meters, well, the unit for resistance is ohms. Now, why this is all relevant is because you already know that electrons move along a circuit, but the question is, well, how do they move? What's making them move? And how well do they move along a circuit? Because we've talked about conductors and insulators, not isolators. And so this Ohm's law sort of tells us about the movement of the electrons within a circuit. The first thing we're going to talk about in any sort of depth is resistance. And so resistance is the degree to which a substance opposes the flow of electric current through it. Now that's a bit complicated, but basically resistance is something that slows down electrons. And so all substances will resist electron flow to some extent. What do you think is something that has relatively low resistance? So maybe pause the video, give that a thought. But if you paused and you remembered metals have relatively low resistance, and that because one of the properties of metals is that they're good conductors of both heat and electricity. Now, you may think that resistance is a bad thing because it slows down our favorite little electrons, but in reality, something that slows down these electrons can actually make use of that energy and convert the energy to something useful. So when we have been drawing circuits, our light bulbs are an example of resistance on a circuit. So as we move to our next slide, we've kind of already talked about this, but conductors, like metals, are very good at allowing electrons to flow freely through the material, whereas insulators like rubber resist electron flow. And so different materials provide different levels of resistance. Here's another way of thinking about it. So we have three people running on a road, and think about maybe this is a race. How many people are going to be passing along this road per second, or this section of the road? Probably a bunch if it's a marathon. I don't know if you've ever seen the Around the Bay race, but those people come en masse. Okay, here's another one. We have a hill with 4 people. Notice they're already more spread out. They look like maybe they're struggling a bit. How many people do you think would be able to go up this hill sort of per second? Are we going to have a big group of people, or are we going to have a few more stragglers? And finally, here is, it looks like a mud pit to me, and there's people wading through the mud pit. Again, another sort of terrain that is offering a lot of resistance to these people. So if you think about our analogy here, the people are our electrons, and they're just trying to wade through this resisting material. So we've already talked about how resistance forces electrons to slow down. And when they slow down, there's actually a transfer of energy to whatever the resistor is. This is really useful because this transfer of energy allows us to convert the energy into either, what we would consider a more useful form of energy, so heat or light. Down here in red, we have different ways we sort of designate resistance. And so the symbol for resistance is R. The unit for resistance is ohms. And we use a little Greek omega letter here to use ohms in short form. And finally, because we're talking about current, when we have a circuit, we can use an ohm meter to measure resistance. Excuse my wobbly lines. So here are a few images of an ohm meter. Basically, they measure resistance. So there's a few factors that you'll need to know that affect resistance. The first is the type of material. You already know this. Some things are good conductors and some things are poor conductors. So copper is an awesome conductor. We also have a cross-sectional area. So basically, how large is the radius or diameter? And so a bigger radius has less resistance than a smaller radius, because basically there's just more space for that for the current to flow through. Then we have length. So a longer wire will have more resistance than a shorter wire. And finally, temperature. So if it's hot, we have decrease in resistance. Okay, so things or electrons can flow better when it's hotter. So these are 4 factors that affect resistance that you're going to need to know. So this looks like a picture of an incandescent light bulb. Now, incandescent light bulbs act as resistors. This filament that's right here is the thing that primarily resists the flow of electrons. And what happens is that resistance allows the electrons to lose some of their energy, and this energy is sort of rerouted into different forms of energy. And so obviously what we get is light. Now, unfortunately, incandescent light bulbs are not very efficient. In all of the energy that comes from the electrons, only about 5% goes towards light, and the rest is lost as other forms of energy, either sound or heat. That's why the light bulbs are so hot. And this is just sort of another slide that's showing that concept, and we'll keep going. So here is our next important terminology, current. You should probably already know what a current is. If you've ever been to a river and said, oh wow, it's moving very quickly, or it's going pretty slowly today, then you know what a current is. The current is the flow of a charge through a circuit. Okay, so it's the flow of something. In this case, our current is electrons. In the case of a river, our current would be of water, right? So current, in the case of circuits, can only move through a complete circuit. So current will not flow unless the circuit is complete. That's something you know already. Additionally, this current is supplied by some sort of power source, okay? In the case of a river, usually it's a matter of gravity. In the case of our current, there's some sort of power source that's pushing the current. And so it's the rate of flow of charge, okay? So it's rate of flow. Over here again, we have some important things for you to remember. The symbol of current is I. It totally does not make sense. I don't know what to tell you other than that's why it is. I'm sure there's a reason, I just don't know what it is. The unit of current is the ampere, and sometimes we call it amps, which we have talked about before in the past. But so we have the symbol, which is I, and the unit, which is ampere. Now, the symbol of amps is A, okay? So we have two different symbols here. We have the symbol of the unit and the symbol of the terminology. Finally, we have an ammeter, which must be placed in series when we're measuring a current. So I've attempted to draw a little circuit over here on the bottom right-hand corner. We have our cell and we have a resistor. And so when I say that the ammeter must be placed in series, I mean you're going to be drawing your little box and your A. Of course, yours is going to look better than mine because you won't have this black line running through it. And so this ammeter is placed in series with both the cell and the resistor. It's all one circuit, one after the other, one route for the electrons to flow. So we've talked about current, we've talked about resistance, and now we need to talk about voltage. So voltage is the big push. It's what makes the electrons move. Okay, so it's the push in electricity. And it only happens in a complete circuit because otherwise, where will the electrons go? Sometimes we call it potential difference. And so you might see these terms used somewhat interchangeably. They're different things, but don't be surprised if you see them both used, okay? And so basically the voltage is sort of supplied by the power source. And it's the measure of the energy carried by a charge, okay? So I like to remember it as the push in the electricity. So the symbol for voltage is V. That's pretty straightforward, not like our current and I situation. The unit of voltage is volts, with, again, the symbol being V, so very straightforward with voltage. And we use a voltmeter placed parallel around a load. So depending on what load or resistor we're talking about, then we're going to place it in parallel. Okay, so what I've drawn over here on the right is our little circuit, and I've actually drawn two voltmeters. There's one placed in parallel around the light bulb, and there's one placed in parallel around the single cell that's here. So they're placed in parallel, which means there's two routes, two or more routes for the electricity to flow. Okay, so here we have a bit of an analogy with water. So we have our three different measurements: resistance, current or amperage, and voltage. I'm going to start on the right-hand side because it's just a bit simpler to talk about. We have one of our factors that determine resistance here, and that factor is radius of the conductor. In this case, our conductor is a pipe, And in one, the radius is constant throughout, and in the other, the radius has a pinch spot where it gets smaller. So this second problem has more resistance because it causes the water to slow down at this pinch spot. Moving to the middle image, we have amperage. Now remember, amperage is the rate of flow. So this pipe is bigger than our pipe on the right. And so our current is greater on the left. So the rate of flow is greater on the left. And finally, our left image shows voltage. Now, I've mentioned the term potential difference or potential energy. And this is sort of a physics term that we haven't gotten the chance to talk about yet, but it basically describes the amount of stored energy that something has. And so one way of storing energy is by having it up high. And so that's what this little line is demonstrating. It's saying that this water is up high, which means it has the potential energy to come rushing out of this pipe. So that's sort of a very simplified way of talking about potential difference or potential energy. And so basically what's happening here is the water, because it's stored high, it can exit the pipe. If you're interested in learning more about potential difference or potential energy, I will absolutely link some websites or YouTube videos for you so that you can find out a bit more about that, because we're not really going into much detail about it right now. Okay, so resistors have a huge, well, really all of them do, but resistors has a very obvious effect on the other measurements of a current. They can be used to control a current as well as potential difference. So in a circuit, electrons have a higher potential difference or higher voltage than when they enter a resistor compared to when they leave the resistor. This is because as they go through the resistor, they use some of the energy to pass through it. Down here I have some diagrams. There's a lot more information than you necessarily need to know. Take a look at it, see if you can make sense of it on your own. Okay, here's where we get to the math problems. We have our Ohm's law triangles, where voltage is equal to current times resistance. Current is equal to voltage over resistance, and resistance is equal to voltage over current. Let's try a math problem. Okay, here are the formulas rewritten with units down here and just the sort of names of it up here. Here's a sample problem. Pause the video now. See if you can use those formulas to find the answer. Okay, so hopefully you paused the video. I've written up the solution. Usually I would work through a whole grasp method of solving this with you, but to be frank, this using my mouse and this pinpoint is driving me crazy. So we have resistance is equal to volume over current. And so we have volume, that's the 2000 volts. We know because it says volts. So by knowing the unit, we know what information we have. We also have amps, and amps the funny one, where it actually means current. So current is 200, or I, and then we simply solve. 2000 divided by 200 is 10. So our resistance is 10, and that's our final answer. Let's go to the next one. Oh, you all already know how to do that, but this is just how to manipulate the formula. Okay, pause the video now and try this one on your own. You may notice that my answer is in the bottom right. So check your answer down here. And if you need any help, let me know. That's the end of the lesson. See ya.